Hello everyone, welcome to my talk. I'm Lijun Wang, a PhD student from the Chinese University of Hong Kong. I will share my project. Here I put 3 keywords in my title. I'm working on multiple object tracking, and I propose a tripartite matching, which is solved by dynamic programming. First of all, let me introduce what is multiple object tracking. Here, as you can see in the demo video, the brightest near circles are the so-called natural killer cell, and this irregular, equivalent to the culture dish with the cancer cell. The natural killer cell keep bumping into the cancer cell, and eventually the cancer cell bursts. So our task is to track the natural killer cell, and the blue points are the detections of the natural killer cell, and the red curves are the estimated path by our tracking algorithm. Multiple object tracking has become more and more popular in various areas, such as human tracking, cell tracking, animals tracking. And there are many multiple object tracking algorithms, but most of them will share these 2 steps, detection stage and association stage. Although different algorithms may have additional steps or perform these 2 stages in different manner, such as separately, hybridly, repeatedly. We would focus on the association stage. There are 2 popular association methods. This reference summarizes 21 participating algorithms in the cell tracking challenge, where 1/3 would based on method A, 1/3 based on method B, and the remaining 1/3 would belong another several different methods. What I want to say is that method A and B is quite popular association methods. Let me give you a quick explanation of method A. Suppose we have 3 cells on the first frame and 2 cells on the second frame. Our task is to match these 2 frames. For example, to determine whether cell L1 match R1 or R2 or just disappear. Here D implies disappear and A means appear. This can be solved by the bipartite graph matching. Method B can construct similar graph. The motivation for our method is that many tracking tasks would rely on the appearance of the particular objects. We try to propose appearance-free method for object without distinguished appearance. And secondly, the method A would fail in some cross-path situations. We try to improve the accuracy. And also we try to reduce the computational cost. So let me first show the results on the real cell video. As you can see, here there are 2 different color curves, blue one and orange one. And the most paths would coincidence, which means that the path by the distant method and our proposed method are the same in most cases, but there are still some different paths. And then if we zoom into this bounding box, we pick 2 cells, and the distant method would say the green cell would follow this path, the red cell follow this path, but our proposed method give different results. The green cell follows this path and the red cell follows this path. So by careful observations, we would prefer this one as the truth. So in other words, the distant method make mistakes when the green cell pass by the green cell to the red cell. So why this is more reasonable? Since that the green cell move faster than the red cell, and it also have a clear direction, but the red cell just something like we're randomly around a point. But the distant method suddenly slow down the green cell and speed up the red cell, so which is not quite realistic. Another case study also shows the power of our proposed method. How can we do it? Now let's go into details of model. First, we define 2 key concepts: the state vector, which consists of the position, velocity, and shape. And we assume it follows Markov process. Another is matching vector. If cell I in frame K move to cell J in frame K plus 1, then the S element would be J. Otherwise, it would be -1. So for 2D case, the matching vector uniquely determines the trajectories of all cells. The space of the matching vector can be written as a union of permutations. then we can write out the likelihood function. So the target is to maximize the likelihood function, where M is taken from this space. And by macro property, we can write in this form. For the particular choice of state vector, this can be further simplified. And with this proposition said that if he can simplify in this way, we can solve it quickly, and such as the position model. The position model would model the position difference as some distribution of, in particular, the distance method would equivalent to assume the residual follow such Gaussian distribution. In addition to put the position into the state vector, we can also put the velocity. And by the relationship between velocity and the displacement, we can get this formula. And if we assume this residual follows such Gaussian distribution, we can get the results. But note that here, this is not possible definite, so we cannot directly use this result. To avoid the problem, we consider to some models. We pick the first two elements, which is equivalent to multiplying this matrix, and we get this results. And you can compare this result with the position model. Also, we can pick the last two elements, which is equivalent to multiplying this matrix, and we get this results. Since we cannot get the instant velocity, so we always take the velocity as the average velocity. And in this case, these two submodels would be equivalent. So we can start from anywhere. And then the probability can be written as in this way, which involves 3 frames. So I call it the tripartite model. And this computational complexity is much larger than bipartite model. So we need to use new method to solve it. And we applied dynamic programming to maximize the likelihood function. Dynamic programming is a recursive procedure which firstly forward calculate and get the maximum value, and then backtracking to get the optimum matching vector. The complexity is determined by the size of such space, which turn out to this order. And for large n, we cannot handle it. So we need to come up with some method to reduce the size. And here are some hints from the bipartite model. We know that the bipartite model will fail if the path crossed, as I showed in the rehearsal video. So, which means that if we change some elements of the bipartite matching vector, we might cover the truth. Then we focus on the permutations of such matching vector. And secondly, the bipartite model will provide us an estimate of the number of disappearing cells. Then we can restrict the number of disappearing cells in this range. Recall that the space of matching vector can be written as the union of some permutations. Then the reduced space can be get by restricting the index, such as fixed ij and restrict d in this range. Then with this reduced space, we can reduce the complexity to this order, which is comparable with the bipartite model. Now next we would present the simulations to show the superiority and the efficiency of our proposed method. We want to imitate this rehearsal video. Here, the closed rectangle represents the culture dish, and the dashed rectangle represents the visible region of the camera, and the cells can move in this closed rectangle, and it can move in or leave out the dash boundary, but it would be reflected back if hit the solid boundary. Then we generate a fixed number of cells uniformly in the closed rectangle and simulate their motions. Then we apply different tracking algorithms and compare the accuracy. The accuracy is measured by the F-score, which is a combination of precision and recall. Here is one result. Here I compared our proposed method, here this 4, with the 2 popular methods, as I mentioned at the beginning. This actually is the method A, this is method B. as you can see, our proposed method would outperform the two competing method, and this one is also outperform. Although this one would be slightly better with a fewer frames. More simulations can be found in our paper, and in our conclusion, we formulate the tripartite matching as maximizing the likelihood of state vector constrained by the position velocity, and we decompose the space of matching vector by the number of discrete cells, and then propose reduced space techniques. Both simulations and real video show the superiority and efficiency of our proposed method. More details can be found in our paper, and thank you for your attention.